If the atmospheric setup building over the central United States right now got you locked in, take a second and subscribe to Orbital View. We are tracking this pattern in real time. The heat, the storms, the grid sitting between them, and what the combination produces when all three arrive at once before the country is ready for it. Drop a comment and tell me, which side of the dome are you on right now? The heat or the storms? Because where you are over the next 2 weeks determines which catastrophe you're walking into. I read every single one. Here is what this investigation covers. A ridge of high pressure so large and so stationary, it functions as an atmospheric wall, and what that wall does to the tens of millions of people living under it. The outer edge of that wall, where the temperature gradient becomes so violent, it acts as a launch track for mesoscale convective systems that can run for hundreds of miles without breaking. The power grid, caught between those two threats, and what the North American Electric Reliability Corporation's own 2026 summer assessment said, in plain language, in a published document, about what happens to specific regions under exactly these conditions. The historical record of what this compound pattern has actually produced. And the three ways this resolves, what each one costs, and what the data will tell us which one we're in. Let's get into it.
Right now, as you're reading the weather headlines, a configuration is assembling over the central United States that the Weather Prediction Center in College Park, Maryland, is calling something specific. Not a summer warm-up, not seasonal heat. An upper ridge axis, the spine of a blocking high-pressure system extending from central Texas north toward the Great Lakes, and it is not moving. The WPC's extended forecast discussion issued on the 30th of May, 2026, named it plainly. A dome of above normal temperatures accompanying a ridge that will drift, their word, toward the southeast through the first week of June, pulling the worst of the heat with it as it goes. I want you to understand what drift means in this context. It doesn't mean leave. It means migrate slowly eastward, expanding its reach as it goes, dragging the heat umbrella across more and more of the country while the edge, the violent storm-generating edge, follows right behind it like a shadow. This is the Ring of Fire pattern. And before I explain the mechanism, let me describe what it looks like from space, because the image is the thing that stays with you. Picture a massive, continent-sized bubble of hot, sinking, bone-dry air parked over the middle of the country. Everything inside that bubble bakes in still, airless heat. The atmosphere inside is capped. There's a lid on it, a layer of warm air aloft that prevents any convection from punching through, so thunderstorms can't form inside the dome. You can be standing in Kansas City in 105-degree heat watching a perfectly clear sky, knowing there's a violent thunderstorm 300 miles away. That storm can't reach you. The dome won't let it in. But along the outer edge of that dome, along the invisible border where the dome's sinking air meets the cooler, moister air being displaced around it, the atmosphere is in a state of furious tension. The temperature contrast there is sharp. Imagine two air masses pressed against each other like tectonic plates, one of them trying to slide over the other. The cooler air undercuts the warmer air on the dome's boundary. It lifts. When moist, unstable air lifts fast enough, it explodes upward into towering cumulonimbus clouds. And when that happens at scale, when it happens along a line hundreds of miles long, what you get is not isolated thunderstorms. What you get is a mesoscale convective system. A wall of storms, organized and self-sustaining, feeding off the temperature gradient the dome itself is creating, and capable of producing winds that exceed 100 miles per hour across a swath the size of a small state. The dome creates the storms. This is important. The storms don't come despite the heat. They come because of it. AccuWeather senior meteorologist Alex Sosnowski described the setup in late June of 2025 during a nearly identical configuration. He wrote that thunderstorms on the fringe of the heat dome are what meteorologists call ring of fire thunderstorms, systems that thrive on the heat and humidity, potentially producing flooding, tornadoes, hail, gusty winds, and a wealth of other dangerous weather phenomena. He noted that intensely high pressure and sinking air are the signatures of a heat dome, and they make it difficult for thunderstorms to form in large numbers inside the dome itself. The violence accumulates at the edge. Hold that image. The dome is a wall. The wall has a perimeter. The perimeter is on fire. Now here's the part most coverage misses, and this is where this investigation earns its title. The first 2 weeks of June are not typically when this pattern locks in with this kind of force. The jet stream is still close enough to the surface in late spring and early June to provide the atmospheric disturbances that keep systems moving, that prevent any single ridge from becoming a parking brake over the middle of the country. By late July and August, the jet stream retreats so far north that heat domes are almost expected. But right now, in the first days of June, this pattern is arriving earlier than the seasonal climatology says it should, and the systems that are least prepared for it are the ones that are going to feel it first. NERC, the North American Electric Reliability Corporation, the grid watchdog for the entire continental United States, released its 2026 Summer Reliability Assessment on May 19th of this year. I've read it. And the language is careful, the way language from an institution is always careful. All assessment areas are expected to have adequate resources to meet normal summer peak demand in 2026. That's the headline. That's what got covered. But here's what didn't get covered. The next sentence, the one that says, extreme heat, drought-driven hydropower reductions, rapid load growth, and variable renewable output continue to pose reliability challenges, especially during prolonged heat waves or when early summer temperatures overlap with planned maintenance outages. Early summer temperatures. Planned maintenance outages. Both of those conditions are active right now. And NERC's own long-term reliability assessment from January of 2026 identified 6 specific regions facing what they called high risk of resource adequacy failures over the next 5 years under extreme conditions. Those regions are MESO, the Mid-Continent ISO, which covers the Central and Upper Midwest, PJM, which covers the Mid-Atlantic and Ohio Valley, Texas RA ERCOT, WEC Northwest, WEC Basin, and CERC Central, which covers the Deep South. Those 6 high-risk regions form a near-complete ring around the center of the country. They are, almost precisely, the states that sit on the outer edge of the Ring of Fire pattern. I sat with that map for a while. Let me put you somewhere specific. It's June 8th. You're in Wichita, Kansas. The overnight low was 83 degrees. That's the overnight low, the coolest the air got in the past 24 hours. You woke up to that. Now it's 2 in the afternoon, and the temperature at the Mid-Continent Airport, recorded by the Kicked Surface Observation Station, is 107 degrees Fahrenheit. The heat index, the feels-like number that accounts for humidity, which is running high on the dome's southern fringe, is 114. The SPC Day 1 convective outlook for your area is a big blank. Clear sky, no storms, no relief coming. Your air conditioner has been running for 31 consecutive hours, and so has everybody else's. This is the flash drought mechanism, and it works faster than most people expect. Flash drought is not a slow, creeping lack of rainfall building over months. It is the rapid onset of drought conditions driven primarily by temperature, by heat that pulls moisture out of every surface it touches with a speed and aggression that normal seasonal drought doesn't match. The National Integrated Drought Information System defines it as drought that intensifies rapidly due to abnormally high temperatures, winds, and radiation, which together increase evapotranspiration and lower soil moisture in days, not weeks. There's a metric that captures this process almost perfectly, and almost nobody outside the agricultural and atmospheric science community uses it. It measures how aggressively the air is pulling moisture out of every surface it touches, every field of winter wheat, every pasture, every drainage tile in the Great Plains soil. Scientists call it vapor pressure deficit. Think of it as the atmosphere's thirst. A high vapor pressure deficit means the air is intensely, almost violently thirsty. It will strip moisture from anything it contacts: crops, topsoil, leaves, livestock. And under a heat dome, with temperatures running 20 degrees above normal, vapor pressure deficit climbs to levels that can damage a corn crop in 72 hours. Not over a season. In 3 days. The 2012 heat wave is the reference case. It's the one researchers keep coming back to because it's the closest thing we have to a controlled experiment in this kind of event. The summer of 2012 was the greatest United States drought since the Dust Bowl of the 1930s. Temperatures in the breadbasket states during May, June, and July exceeded all previous records in the observational database. Corn, soybean, and wheat crops failed. The direct food price increases caused by that single event reached $41 billion. Economy-wide analysts believe the total cost was closer to $80 billion. And research published since has found that what used to be a once-per-century heat event in the American breadbasket is now expected to occur once every 5 years. Not once every 100, every 5. But even the 2012 event didn't begin in the first week of June. And here's where the compound problem emerges, because what I haven't told you yet is what happens to the power system serving Wichita while your air conditioner runs for 31 consecutive hours. ERCOT, the Electric Reliability Council of Texas, has seen this scenario before. In June of 2021, during a heat wave that followed the catastrophic February freeze that had already pushed the Texas grid to collapse, ERCOT issued a conservation alert. The grid was projecting peak demand of 73,000 megawatts, far above the June record of 69,123 megawatts set between 4 and 5 in the afternoon the year before. They asked users to set thermostats to 78 degrees or higher in June, during a heat wave. The people they were asking had already been through a winter where the grid failed and people died. Now multiply that scenario, not Texas alone. Texas plus Oklahoma plus Kansas plus Missouri plus Indiana plus Ohio. All of them inside the dome at the same time. All of them running peak air conditioning demand simultaneously, for days on end, in temperatures 20 degrees above the seasonal baseline. The grid doesn't see this in July, when the systems are running at full summer capacity and all planned maintenance has been completed. The grid sees this in early June, when some generating units are still offline for seasonal maintenance, when the shoulder season staffing and operational protocols haven't fully transitioned, when the people managing the system were told, by every model and every seasonal outlook, that the real stress wouldn't arrive until mid-July. NERC's Director of Reliability Assessment and System Analysis, John Mora, said something at a webinar in late May of 2026 that I think is worth quoting directly. He said, "The improved conditions we're seeing shouldn't be interpreted as saying that overall reliability risk is declining. While we've made a lot of progress bringing resources online, we do see some risks emerging." And then he said, and this is the part that matters, that peak demand across all assessment areas had climbed more than 11 gigawatts in the prior year. 11 gigawatts of new demand on a grid that was already being called tight under extreme conditions. 11 gigawatts is roughly the output of 11 large nuclear power plants added in a single year. Mostly from data centers and AI infrastructure that wasn't there 2 years ago. So inside the dome, you have flash drought developing in days, not weeks. Temperatures 20 degrees above normal, potentially for 10 to 14 days straight. Overnight lows that don't allow the human body or the built environment to recover. And a power grid that, by the North American Electric Reliability Corporation's own published assessment, has adequate resources for normal conditions, but faces what NERC calls reliability challenges under exactly these extreme conditions, in exactly this region, in exactly this seasonal window. That's not a hypothetical. That's the scenario the grid managers are looking at this week. Now step outside the dome. Move to the perimeter. Because what happens? There is a completely different kind of catastrophe, and it arrives without the warning that heat gives you. You're in Indianapolis or Columbus or Minneapolis or St. Louis. Cities on the dome's edge, sitting in the volatile transition zone where the hot capped air mass meets the cooler, moister air being pushed outward. The temperature where you are is 91 degrees. Warm, but not the scorching triple-digit temperatures inside the dome's core. You have some humidity. You have a convective environment that's building by the hour as the afternoon progresses. And somewhere to your west, a disturbance, a shortwave trough moving off the Rockies, is providing the forcing mechanism, the trigger, that the atmosphere has been waiting for. By 4 in the afternoon, towering cumulus clouds are forming on the horizon. By 5, they've turned into cumulonimbus, and by 5:30, the CLOT NEXRAD radar at Chicago and the KILN NEXRAD at Wilmington, Ohio, are both lighting up with reflectivity values that the forecasters at NWS Chicago and NWS Wilmington are watching closely. Not just for isolated severe thunderstorms, for organization. For the Bow echo signature that tells you a mesoscale convective system is forming. A mesoscale convective system, an MCS, is what you get when a collection of individual thunderstorms organizes into a single coherent system that can sustain itself for hours. The physics that drives it are self-reinforcing. The storms produce a cold pool, a mass of cold, dense air that has been pulled down from altitude by precipitation. That cold pool spreads out beneath the storm line like a plow, undercutting the warm, moist air ahead of it and forcing it to rise rapidly along the leading edge. This creates new convection, which creates more cold pool, which pushes the leading edge further forward. The system feeds itself, and it doesn't need favorable atmospheric conditions to last, the way a supercell does. It creates its own conditions. It is, in a sense, its own weather system. The SPC's formal definition of a derecho, the most destructive type of MCS output, requires a wind damage swath at least 250 miles long, with gusts of at least 58 miles per hour along its full length and several well-separated gusts of 75 miles per hour or greater. What makes a ring of fire MCS particularly dangerous is that the temperature gradient at the dome's edge provides a constant fuel source. The system doesn't have to weaken as it moves. It can actually intensify because every mile it travels brings it into contact with more of that volatile boundary zone. The sharp temperature contrast between the dome air and the surrounding air acts like a track, and the MCS runs along it. August 10th, 2020. I need you to know this event because it is the template. The storm began forming in eastern Nebraska and southeastern South Dakota during the early morning hours. The Storm Prediction Center in Norman, Oklahoma, had been monitoring conditions since the prior day. By mid-morning, a line of thunderstorms was moving southeast across Iowa. By 11:50 in the morning, the Marshalltown Airport recorded a gust of 99 miles per hour. 2 minutes later, the town of LeGrand recorded 106. At 12:28 in the afternoon, a weather station in Atkins, Iowa, in eastern Benton County, recorded 126 miles per hour. That is the strongest wind gust ever measured in the state of Iowa. The NWS radar site at Davenport, KDVN, showed a bow echo that was textbook. One of the most pronounced and clearly defined bow signatures forecasters at NWS Quad Cities had ever seen. By the time the storm reached Cedar Rapids at 12:30 in the afternoon, it wasn't weakening. It was still at peak intensity because it was still running along the edge of the high-pressure ridge that had been building over the region. In roughly 90 minutes, eastern Iowa experienced some of the most intense straight-line wind damage in American history. Cedar Rapids lost upward of 70% of its urban tree canopy. 4.4 million trees were destroyed across the state. 850,000 crop acres were a complete loss. The U.S. Agriculture Department estimates Iowa farmers were unable to harvest at least 850,000 acres of crops that fall. The state lost 70 million bushels of grain storage capacity, and 2 million people lost power, with outages in the hardest hit parts of Lynn County lasting a full 10 days. The total damage from 14 hours of storms, $11.5 billion. The costliest thunderstorm event in United States history. It held that record until recently. Now here's what I want you to sit with. The 2020 Iowa derecho was a single event, one day. One passage of 1 MCS. The ring of fire pattern in the first 2 weeks of June doesn't produce 1 MCS. It produces a new one nearly every day, as the dome persists and the edge of the dome cycles through disturbances that trigger fresh convective organization. Every evening, as the afternoon heating peaks and whatever shortwave is available triggers convection, the MCS factory at the dome's perimeter starts another run. It doesn't reset to zero. The ground is already saturated, or already dry, depending on where you are. The infrastructure that took a hit the night before hasn't been repaired. The power that went out at 3 in the morning is still out at 2 the following afternoon when the next line forms. This is the compound mechanism, and it's the part that the daily weather coverage doesn't capture. Because the daily weather coverage covers today's storms, not the cumulative effect of 7 straight days of them. Let me get into the physics here, because the physics is what explains why this pattern produces more violent storms at its edge than almost any other atmospheric setup. I'm going to say this in plain language first, and then give it the technical framing. Picture 2 air masses sitting next to each other. One of them is sitting inside the dome, hot, dry, dense in the lower atmosphere, capped by warm air aloft. The other is outside the dome, cooler, much more humid, loaded with the kind of energy that becomes severe weather when it gets lifted. These 2 air masses don't mix easily. They press against each other along a boundary. And the steeper the temperature difference across that boundary, the bigger the contrast between what's inside the dome and what's outside it, the more explosive the convection becomes when something forces air across that line. Under a 20 degrees above normal heat dome, that temperature gradient is extraordinary. You can have a 104-degree air mass in central Kansas pressing against a 78-degree air mass in Missouri, separated by a line that's maybe 30 miles wide. That's a 26-degree temperature difference across 30 miles. In meteorological terms, that's a baroclinic zone, a band of sharp temperature contrast that concentrates available potential energy. Think of it as a compressed spring. Everything along that line is coiled, loaded, waiting for a trigger. The trigger is usually a shortwave trough. A shortwave is a small-scale wave in the upper atmosphere, moving through the larger-scale flow. When a shortwave moves over a baroclinic zone, like the one at the dome's edge, it provides the lift needed to release all that stored energy. The air along the boundary goes up fast. The convective available potential energy, the CAPE, which is essentially a measure of how much rocket fuel the atmosphere has loaded into the lower levels, is extremely high along the dome's perimeter, precisely because the temperature contrast is so extreme. Values of 4,000 to 5,000 joules per kilogram of CAPE are not unusual in this setup. To put that in context, the threshold for severe thunderstorms is typically above 1,500 joules per kilogram. 4,000 joules per kilogram is, in the language of Storm Prediction Center forecasters, loaded. It's the kind of environment where a storm that manages to get organized can reach incredible intensity very quickly, because the energy available to it is nearly unlimited as long as the dome maintains that temperature contrast. And this is what makes the ring of fire pattern self-sustaining at the perimeter. The dome doesn't weaken the storms on its edge. The dome is the reason for them. As long as the ridge persists, as long as the central high-pressure system maintains its anomalous strength, The temperature gradient at its edge remains steep. The cape remains elevated, and every disturbance that moves through the upper atmosphere in the vicinity of that gradient has the potential to trigger the next major MCS. The 2025 Ring of Fire event in June and July is instructive here. AccuWeather meteorologist Alex Sosnowski documented how the thunderstorms forming on the dome's edge erupted first over the northern plains and Midwest, then took over portions of the Northeast, then migrated to the Southwest and Central Plains, following the dome's edge as the system slowly migrated. Locally severe thunderstorms continued day after day. Severe weather, with high winds, flooding rain, and tornadoes, impacted different regions sequentially, tracking the dome's perimeter as it moved. What we're looking at in early June 2026 is that same factory, but with a ridge that's positioned to lock over the central United States at the exact moment when the seasonal climatology says it shouldn't be this strong yet. The SPC's Day 4 through 8 convective outlook from the end of May 2026 explicitly identified that a ridge is forecast to move from the north-central U.S. on Monday into the Great Lakes by Wednesday, and that in the vicinity of this ridge, an axis of moderate to strong instability is forecast to develop, meaning the cape is already loading along the edge before the pattern fully sets. I want to be honest about what this means in terms of specificity. The models are in reasonable agreement about the large-scale pattern, the ridge, its position, the dome of anomalous heat. The specific day-by-day placement of individual MCS events is harder. Convective initiation is notoriously difficult to forecast beyond 48 to 72 hours. What the models can tell you, and what the SPC's medium-range guidance confirms, is that the atmospheric setup for repeated severe weather events along the dome's perimeter will be present throughout the first 2 weeks of June. What they can't tell you with confidence is which cities on which specific days. That uncertainty is not reassurance. It's the shape of the threat. When you can't tell someone in Indianapolis whether the 98-mile-per-hour wind line is coming Wednesday or Thursday, the only rational response is to be prepared for both. I keep coming back to 2012, not because it's the worst case, it isn't, not by every measure, but because it was the first time in the modern observational record that both sides of this compound pattern manifested at full intensity across the full breadth of the country at the same time. Inside the dome, the worst drought since the Dust Bowl, crop losses of $41 billion, temperatures that broke records set in the 1930s. At the dome's edge, the June 29th derecho, which was at the time the most destructive, fast-moving severe thunderstorm complex in North American history. Let me walk you through the June 29th event specifically, because the sequence of what happened in those 18 hours matters. The storm formed on June 29th, 2012, beginning around 10 in the morning local time in northern Indiana and northern Illinois, where a line of storms had been building along the boundary of the heat dome that had parked over the central states for weeks. The SPC had a moderate risk of severe weather posted for the Ohio Valley, but the system wasn't at full intensity yet when it crossed into Ohio. It was at full intensity by 3:37 in the afternoon, when the SPC increased the threat level to moderate risk for Ohio, West Virginia, and neighboring states, and issued explicit warnings about an extreme wind threat. The storm crossed the Columbus, Ohio area at approximately 5 in the afternoon. The NWS Columbus office recorded winds to 82 miles per hour. The Columbus area saw severe damage to the power grid in Franklin, Delaware, and Licking counties, 3 of the most populated counties in central Ohio. The storm did not stop at the Appalachians. Heat dome derechos don't stop at mountain ranges, because the heat dome doesn't stop at mountain ranges. The energy driving the system was the temperature gradient, and that gradient existed all the way to the Atlantic coast. Despite the mountainous terrain, which normally dissipates storm energy through friction and a disruption of flow, the hot, humid air mass and extremely high instability allowed the storms to maintain what the NWS documentation describes as high intensity all the way through the mountains and into the mid-Atlantic. By late evening on June 29th, the storm had covered 700 miles. Wind gusts of 80 to 100 miles per hour had been recorded across Ohio, West Virginia, Maryland, and Washington, D.C. The NWS Weather Forecast Office in Sterling, Virginia, recorded June 29th as the hottest June day ever measured at Washington Dulles Airport, 104 degrees Fahrenheit in the city, 102 at Dulles. And then the derecho hit at night, in the dark, after a day of record heat had already left millions of people exhausted, and their air conditioning units running at maximum capacity. The morning of June 30th, 4.2 million customers without power across 11 states and Washington, D.C. That number came from utility reports compiled the morning after. The U.S. Department of Energy's Office of Electricity and Energy Reliability launched a review specifically because of what happened next. Because 4.2 million customers without power in the aftermath of the hottest June day in recorded history at the nation's capital is not a power outage event. It's a public health emergency. Heat claimed 34 lives in areas without power following the derecho. 34 people, killed not by the storm's winds but by what came after, by the inability to cool themselves in 100-degree heat without air conditioning, in the dark, in the days it took the utility companies to restore service. The DOE review found that restoration efforts took 7 to 10 days in many cases, complicated by the damage to cellular telephone infrastructure, which made it difficult for crews to receive storm reports or coordinate repair efforts. In central and eastern West Virginia alone, 670,000 customers lost power. It took over a week for most of them to get it back. Now, the summer of 2012 also saw a series of derechos. Not one, a series. The first on June 29th is the one most people remember. But it was followed by 3 additional derechos in July and a final event in Chicago in early August. The DOE review noted that the derecho occurred during a period of heat wave and that this combination, storm damage plus heat, was a unique nature compared to typical summer seasonal storms. It was unique then. It's become the template since. 2012's total heat wave losses, including the agricultural damage from the drought and the derecho damage combined, were estimated at $30 billion. That's the combined cost of the worst drought in modern American history and the most destructive derecho on record at the time. And the research published in the years since has found that the probability of events like the 2012 heat wave has increased by a factor of 20. 20 times more likely, not 20% more likely, 20 times. That number comes from researchers at Deep Sky Climate, who noted that heat waves like 2012 used to occur once every 100 years. They now expect them once every 5. Which means, mathematically, in the next 10 years, you can expect to see 2 of them. And the one building right now, in the first week of June 2026, is arriving earlier in the season than 2012 did. At a time when the grid is carrying more load than it was in 2012. With a CAPE environment along the dome's edge that the SPC's medium-range guidance is already flagging as moderate to strong.
The 2012 summer showed us what one derecho in a heat dome did to 3.7 million customers' power for a week. We're now tracking a pattern that could produce that scenario repeatedly, in sequence, across different sections of the dome's perimeter, while the interior of the dome simultaneously pushes air conditioning demand to record levels and drives flash drought conditions into the breadbasket states within days. And the first 2 weeks of June are just getting started.
And here's where the story takes a turn that most of the coverage of this pattern is going to completely miss. Because when you talk about a ring of fire weather event, the conversation almost always splits into 2 separate tracks. The heat people cover the heat. The storm people cover the storms. The grid people cover the grid. Nobody puts them in the same room and asks what happens when all 3 are active at the same time. When the interior heat is pushing demand to record levels, the edge storms are taking down transmission infrastructure, and the grid between them is already running at or near its operational ceiling. Let me show you what that looks like and why it matters more than either the heat or the storms alone. The power grid in the central and eastern United States is not one system. It's 3 separate interconnections: the eastern interconnection, the western interconnection, and ERCOT in Texas, which operates as its own island by design. Within those interconnections, the grid is managed by regional transmission organizations and independent system operators. The relevant ones for the Ring of Fire zone are MESO, which covers the upper Midwest and Central states, PJM, which covers the Mid-Atlantic and Ohio Valley, and ERCOT, which covers most of Texas. NERC's 2026 Long-Term Reliability Assessment identified all 3, MESO, PJM, and ERCOT, as high-risk regions for resource adequacy failures over the next 5 years. Not elevated risk, high risk. The difference matters. High risk means that under extreme weather conditions, NERC projects that planned resources would result in energy shortfalls exceeding adequacy targets. The target is that the grid has enough reserve capacity that even if a major generating unit trips offline unexpectedly, demand can still be met. High risk means that margin disappears under extreme conditions. And extreme conditions, in NERC's language, means a heat wave, not a catastrophic multi-week heat dome, a heat wave. The threshold for extreme in their modeling is a multi-day event with temperatures significantly above normal across multiple states simultaneously. What's building in the first 2 weeks of June 2026 is, by any reasonable definition, that event, in 3 of the 6 regions NERC flagged as high risk in the same breath. But the grid's vulnerability in this pattern isn't just about demand outrunning supply inside the dome. It's about what the storms on the dome's perimeter do to the transmission infrastructure that moves power from where it's generated to where it's needed. Think about how the grid delivers electricity over long distances. It uses high voltage transmission lines. The big towers you see crossing farm fields and mountainsides, carrying power at hundreds of thousands of volts over distances of hundreds of miles. Those lines are the arteries. When a derecho comes through with 90-mile-per-hour winds, it doesn't just knock out local distribution lines. It has the potential to bring down the transmission towers themselves. And when a transmission tower falls, not a distribution pole, but a major steel lattice transmission tower, the repair timeline is measured in weeks, not days. The June 29, 2012 derecho was specifically studied by the Department of Energy's Office of Electricity Delivery and Energy Reliability for this reason. Their review found that within 11 states and Washington, D.C., the morning after the storm, 4.2 million customers were without power. Restoration in many areas took 7 to 10 days. And the review identified something the daily coverage missed. The cellular telephone infrastructure had also been damaged, which meant the utility crews trying to coordinate repairs couldn't communicate effectively, which slowed restoration, which extended the period during which millions of people were without power. During a heat wave, there's a term in emergency management for this kind of cascading failure, a compound event. Not two bad things happening at once. Two bad things happening at once, where the second makes the consequences of the first dramatically worse, and vice versa. The heat makes the power outage more dangerous. The power outage makes the heat more dangerous. The storm that caused the power outage was itself made more intense by the heat dome. The heat dome is also causing the air conditioning demand spike that's pushing the grid to its ceiling. Every thread in this story connects back to every other thread. This is not 4 separate problems. This is one problem with 4 faces. The DOE review from 2012 was careful to describe the event as unique compared to traditional summer seasonal storms. That was accurate in 2012. I don't think it's accurate anymore. The pattern that produced the 2012 compound event has become more frequent. The probability of the heat dome component has increased by a factor of 20 since the 1990s. The infrastructure being served by the grid, the data centers, the EV charging networks, the electrified industrial loads, has expanded dramatically. NERC's long-term assessment found that summer peak demand could surge by 224 gigawatts over the next decade. That number is 69% higher than what they projected just 1 year prior. 69% revision in a single year. Either the demand growth is accelerating faster than anyone modeled, or the modeling has been systematically missing something. Either way, the grid sitting between the heat dome and the storm perimeter is carrying a load that didn't exist at this level 2 years ago. There's a story inside the heat dome that isn't getting told yet, because it moves more slowly than the temperature records and the power grid alerts. But it will be told in October when the USDA crop surveys come out, and by then it'll be too late for this year's harvest. The first 2 weeks of June are a critical window for corn and soybean development in the central United States. Corn is typically in its V6 to V10 development stages during this period in most of the Corn Belt, meaning it has 6 to 10 leaf collars, it's roughly knee-high, and it's in the rapid vegetative growth phase that sets up the yield potential for the entire season. Soybean is in early flowering in the southern Corn Belt and late vegetative growth in the north. These growth stages are among the most sensitive to heat and moisture stress in the entire crop calendar. A study published in Nature Geoscience in June of 2025 found that flash droughts accompanied by extreme heat drive more severe and prolonged impacts on global ecosystems than either drought or heat alone. The compounding effect is not additive, it's multiplicative. When soil moisture is depleted rapidly by high temperatures and high vapor pressure deficit, and that depletion coincides with peak vegetative growth stages, the damage to yield potential can be locked in within 72 hours. You can subsequently get rainfall, and the crop will have already been compromised in ways it can't fully recover from. The 2021 Pacific Northwest heat dome is the most dramatic recent illustration. The heat dome that parked over the Pacific Northwest in late June and early July of 2021 produced peak temperatures that rose to 4 standard deviations above normal, which is almost statistically unprecedented in a Gaussian distribution of historical temperatures. In parts of the Willamette Valley, farmers experienced 100% crop loss. The USDA climate hubs documented that in extreme temperatures, plants cannot transpire and they have trouble cooling down. Even with plentiful water in the soil, they will not use it to cool themselves because of a stress response that causes them to close the pores on their leaves. Some crops like blackberries and raspberries pulled water from their fruit, making them soft and unsaleable. Some orchards experienced complete fruit drop. That event covered 3 million square kilometers in North America. What we're tracking in June 2026 is centered on a different region, but the mechanism is identical. Anomalous heat of sufficient intensity and duration to trigger crop stress responses that override the plant's normal cooling mechanism, combined with a moisture deficit that removes the soil water buffer the plant would otherwise draw on. In 2012, the failure of corn, soybean, and wheat crops caused rapid price increases up the entire food chain, including meat and processed foods. The sweltering temperatures of spring and summer that year contributed to devastating crop failure, causing $41 billion in losses nationally. That was from a drought that developed over months. Flash drought, the kind the first 2 weeks of June are capable of inducing, can produce similar agricultural damage in a fraction of the time. And here's the compound connection that connects the agriculture story back to the grid story. The agricultural response to heat stress increases regional water demand. Irrigation systems, which in the central states are substantial, Kansas alone has more than 3 million acres under irrigation, draw heavily on both groundwater and surface water when heat and flash drought conditions develop simultaneously. That irrigation load adds to the electrical demand on the regional grid. Pumping systems run longer. Processing facilities run harder. And all of that additional load arrives on a grid that's already being pressed by residential air conditioning demand. It's the same hand pressing down on multiple levers at once. The levers are connected. And when the hand presses down in early June, before the grid is fully transitioned to summer operating protocols, the pressure reaches components that weren't designed to absorb it. Let me bring this forward to June 2025, because last summer's events are both a warning and a data point that this pattern had a dry run. On June 19th through 22nd of 2025, a significant tornado outbreak and long-lived derecho affected large portions of the northern United States and southern Canada, producing what the Storm Prediction Center's formal record now documents as widespread destructive winds, numerous tornadoes, large hail, and flash flooding across the Great Plains, upper Midwest, and parts of the northeastern United States. The event lasted 4 days. The highest wind gust recorded in the derecho component was 120 miles per hour in Beltrami County, Minnesota. An EF5 tornado, with winds exceeding 210 miles per hour, struck Enderlin, North Dakota on June 20th. Maximum rainfall from the event reached 6.5 inches in Chenango County, New York. 7 people died. Now, this event occurred during a period when a heat dome was building over the central and eastern United States. It was structurally a ring of fire setup, storms erupting on the edge of a strengthening high-pressure ridge. The AccuWeather coverage at the time described how the thunderstorms would take on a ring of fire effect, erupting first over parts of the northern plains and Midwest, followed by the Northeast, finally the Southwest and Central Plains. And here's the detail I want you to hold. The 2025 event was considered a major weather disaster. The damage total exceeded $875 million. 7 deaths. It dominated weather coverage for days. It was called extreme. It was called historic. Then the pattern broke, the ridge moved, and the attention moved with it. What happened in June 2025 was not the worst-case ring of fire scenario. It was a ring of fire event where the ridge was strong but not locked, where the blocking pattern wasn't as persistent as what the models are now indicating for the first 2 weeks of June 2026. The 2025 event produced big numbers because it was a big event. But the atmospheric setup for the current period is more entrenched. The temperature anomalies are larger, and the duration of the pattern is expected to be longer. I want to be careful here, because I'm not claiming that June 2026 will definitively produce more damage than June 2025. Convective meteorology doesn't work that way. A more extreme setup doesn't always produce more extreme damage, because a dozen other factors determine where specific storms track, how much population they encounter, and what infrastructure is in their path. What I can say, what the data supports, is that the atmospheric preconditions for a more extreme compound event are present at a higher level during this period than they were in June 2025. The SPC updated its formal wind intensity guidance in March of 2026, introducing new conditional intensity groups to their severe weather outlooks. The new system now includes 3 wind intensity levels for specific areas. No level for mostly less than 75 miles per hour gusts, level 1 for gusts greater than 75 miles per hour, level 2 for bow echoes or derechos with gusts potentially greater than 85 miles per hour, and level 3 for high-end derechos with gusts likely greater than 95 miles per hour. SPC meteorologist Evan Bentley described the new system as a smarter way to be prepared and stay safe. The system didn't exist last June. It was created precisely because the old system, categorical risk levels, without wind intensity specification, wasn't giving people enough information to make decisions in rapidly evolving derecho events. That the SPC felt it necessary to build this new guidance system says something about where we are in our understanding of these events. The threat has become specific enough and serious enough that the existing tools weren't adequate. Here's the piece of this that I think deserves more attention than it's getting, and I want to be direct about why. The mutual aid system that handles power restoration after major weather events was never designed for a simultaneous multi-region compound event. After a hurricane, the regional utilities send crews to the damaged area from across the country. After a tornado, the same thing happens. The logic is that the rest of the country is unaffected. It has spare capacity of crews, equipment, and materials that can be redirected to wherever the damage is. This system has worked well for decades because, historically, catastrophic weather events in the United States have tended to be geographically concentrated. A hurricane hits the Gulf Coast, a derecho hits the Midwest, the rest of the country mobilizes. The ring of fire pattern breaks that assumption. When the dome persists for 2 weeks and the storm perimeter cycles through daily MCS events, it doesn't hit one region. It works around the edge of a feature that covers most of the central and eastern United States. Indiana gets hit Monday, Ohio gets hit Tuesday, Missouri gets hit Wednesday, Minnesota gets hit Thursday. Then the cycle restarts. And none of those events is isolated enough or far enough from the previous event for the mutual aid system to fully reset between them. In 2012, the DOE review documented this problem explicitly, though in a more limited geographic scope. The aftermath of the June 29th derecho created a situation where utility companies in Ohio, West Virginia, Virginia, and Maryland were all simultaneously seeking assistance. Crews from outside the region began arriving, but the coordination was complicated by the cellular infrastructure damage. The NWS office in Charleston, West Virginia, described receiving support from neighboring NWS offices in Pittsburgh and Jackson, Kentucky, in the days following the event because their own communication capacity was compromised. Now multiply that scenario across 7 or 8 affected states over a 2-week period. The inventory of linemen in the United States is finite. The inventory of replacement transmission towers, the specialized heavy lift equipment required to erect new ones, is even more finite. The supply chain for certain transformer types runs months, not days. These are not hypotheticals from disaster planning exercises. These are documented constraints that came up in the DOE's 2012 review and have been discussed in NERC's reliability assessment since. The specific concern NERC raised in its 2026 assessment about maintenance overlap risk, the scenario where early summer heat coincides with planned maintenance outages, reducing available capacity, is exactly this problem described from the supply side. If a generating unit is offline for scheduled maintenance in early June and a heat emergency develops, the utility can try to bring the unit back online early, but that takes time, and in a rapidly developing heat event, time is the one thing you don't have. This is why the first 2 weeks of June mattered differently from the last 2 weeks of July. In July, the grid is transitioned. Maintenance is largely complete. The operational protocols are on full summer footing. In early June, you're catching the grid in a transition state, not fully summer, not fully spring, with the most extreme atmospheric setup of the year potentially arriving ahead of schedule. I've been focused on infrastructure, on agriculture, on the mechanics of the storm system, because those are the threads that connect this investigation's thesis. But there's a human thread running through all of this, and I want to spend time on it before we get to the implications section. Heat kills more Americans annually than any other weather phenomenon. Not tornadoes, not hurricanes, not flooding. Heat. And it kills disproportionately in the first major heat event of the season, which is what the first 2 weeks of June represent for most of the country, because the human body hasn't acclimatized yet. The acclimatization process takes 7 to 14 days of exposure to high heat for the cardiovascular system to adapt. Someone who spends a 2-week heat dome in mid-July is physiologically different by day 12 than they were on day 1. Someone who encounters the first extended heat event of the year, which begins in June, hasn't had that 14-day adaptation window. This is documented in the emergency medicine literature and in the CDC's surveillance data. The highest per capita heat mortality typically occurs during the first heat wave of the season, not the hottest one. The July 23, 2025 heat dome that affected approximately 160 million Americans, tracked by NOAA's Surface Observation Network and documented in the AccuWeather coverage, was brutal, but the body had context for it. June heat, arriving before full acclimatization, arrives without that context. The compound dynamic that emerges when you add the power outages on the dome's perimeter is what makes the 2012 scenario so relevant. The NWS service assessment of the June 2012 event made this explicit. The The storm was followed by 100-degree heat in areas without power. 34 people died of heat in areas without power following the derecho, not during the storm, after it, in the days when the power was out and the temperature was still 100 degrees. Those 34 deaths are a floor, not a ceiling. They represent confirmed, directly attributed heat fatalities in the specific areas studied by the NWS assessment team. They don't include the excess mortality from heat-related cardiovascular events that gets captured in all-cause mortality data weeks later. They don't include the hospitalizations. They don't include the chronic health impacts in elderly and immunocompromised populations that don't show up in immediate mortality statistics. And here's a connection that should be in every briefing about this event and isn't. The people most vulnerable to heat mortality are overwhelmingly the people least able to self-rescue during a power outage. Elderly residents, people with limited mobility, people in lower-income housing without structural insulation or window units, people in urban heat islands where the ambient temperature already runs 5 to 7 degrees higher than the surrounding countryside. These populations are disproportionately present in the older housing stock of Midwestern cities like St. Louis, Indianapolis, Cincinnati, Columbus, and Detroit, cities that sit squarely on or near the dome's perimeter, in the zone of maximum storm exposure. So the scenario that this pattern creates in its most extreme form is not simply a heat story or a storm story. It's a scenario in which the people at greatest risk from the heat are concentrated in the cities most exposed to the storm damage that causes power outages that makes the heat lethal. The cities on the ring are not random. They're there because the temperature gradient concentrates the storm risk exactly where the transition from hot interior to cooler exterior reaches its maximum slope. And the people in those cities who are most vulnerable to the compound effect, heat plus power outage, are there because of the geography of housing cost, urban density, and infrastructure age that shapes every major American city in the industrial Midwest and Mid-Atlantic.
This is not a natural disaster, cleanly separated from everything else. It's a natural system, interacting with the specific vulnerabilities of the built environment and the population it contains. And the natural system is operating at intensity levels that the built environment was never designed to absorb.
Let me take you deeper into the atmospheric mechanics, because understanding why this particular ridge is so persistent is understanding why the first 2 weeks of June are going to feel so unlike what normal early summer weather looks like. In a normal early June atmosphere, the jet stream, the river of fast-moving air at altitude that steers weather systems across the continent, is still close enough to the surface to provide what meteorologists call forcing. Forcing is the mechanism that keeps weather systems moving. A short wave embedded in the jet stream pushes a frontal boundary through a region, temperatures drop, the heat breaks, and the next weather system begins its approach. The cycle repeats every 5 to 7 days in a healthy, mobile pattern. You might get some hot days, but they don't last 2 weeks because the jet stream keeps moving things along. A blocking pattern interrupts this cycle. Think of a blocking high-pressure ridge as a boulder in a river. The water, the jet stream, can't go through it, so it goes around it. And sometimes when the ridge is strong enough and positioned correctly, the jet stream splits into 2 branches, one going far to the north around the top of the ridge, one diving south around the bottom. The weather systems that would normally move through the middle of the country get steered around the outside of the ridge instead, and whatever is sitting beneath the ridge doesn't move. The heat dome under a blocking ridge isn't just persistent because the high pressure is strong. It's persistent because the atmospheric flow has essentially rerouted around it, leaving the region underneath in a state of stagnant recirculating air. Omega blocks are the specific configuration meteorologists most fear in this context. Named for the Greek letter because of what they look like on upper air charts. A large ridge flanked on both sides by deep troughs, forming the shape of an inverted omega. They are the most stable blocking configurations in the atmosphere. When an omega block establishes itself over the central United States, the heat dome beneath it can persist for 2 to 3 weeks, and the storm activity on both flanks of the ridge becomes intense and repetitive. The left flank gets one set of systems cycling through, the right flank gets another, and the interior bakes. This is the configuration the Weather Prediction Center's extended forecast is describing for the first half of June 2026. Not explicitly called an omega block in the current guidance. That specific designation depends on the depth and symmetry of the flanking troughs, which the medium-range models haven't fully resolved. But the structural elements are there. A ridge axis from central Texas to the Great Lakes, a trough digging into the southwest, low pressure and frontal boundaries to the north. The WPC's extended forecast discussion from May 30th described precisely this architecture. An upper ridge extending from central Texas to the Great Lakes with a dome of above normal temperatures, and low-pressure troughs upstream that would bring prolonged wet to the southern high plains while the ridge drifts slowly east. Slowly east. That's the key phrase. In a mobile pattern, the ridge would pass through in 3 or 4 days. Slowly east means this feature is not moving at normal speed. It's dragging. And the longer it drags, the more heat accumulates underneath it, the more flash drought develops, the more MCS events cycle through the perimeter, and the more cumulative damage accumulates to both the infrastructure and the people living in the zone. The NWS office in College Park, the Weather Prediction Center, uses a phrase in its extended forecast discussions that I always look for when I'm trying to understand how confident the forecasters are. The phrase is uncertainty remains. When you see it, it means the models are in reasonable agreement on the large-scale pattern, but haven't fully resolved the timing and placement of specific events. The May 30th WPC discussion had it. At mid-levels, a ridge is forecast to move from the north-central U.S. on Monday into the Great Lakes by Wednesday. That's confident. That's the large-scale feature. But the specifics of where the MCS events go, which cities, which nights, that's where the uncertainty lives. I want to be precise about that, because precision in what we know and what we don't know is what distinguishes this kind of investigation from scaremongering. The large-scale pattern is established. The elevated severe weather risk along the dome's perimeter throughout the first 2 weeks of June is established. The heat anomaly inside the dome, temperatures running 20 degrees above normal in the core, is established. The grid vulnerability under extreme heat conditions in the affected regions is documented by NERC. What is not established and what cannot be established at this range is the specific magnitude and geographic footprint of any individual event within the pattern. The pattern is real. The specific events within the pattern will resolve on their own timeline. Here's what I haven't told you yet about how MCS events compound over an extended blocking pattern, because this is the piece that pushes the first 2 weeks of June from a serious weather event into something genuinely unprecedented in terms of its aggregate impact. A single derecho, August 10, 2020, Iowa, was $11.5 billion, one event, 14 hours. A single pass. But in a persistent ring of fire blocking pattern, the atmosphere doesn't produce one derecho. It produces a series. The term researchers and forecasters use for this is serial derecho activity, multiple organized convective systems cycling through a region over an extended period, each one driven by the same underlying temperature gradient, each one tracking along the same general swath at the dome's perimeter. The summer of 2012 documented this directly. The first derecho, June 29th, was the most destructive, but it was followed by 3 additional derechos in July and a final event in August. Each subsequent event moved through terrain where the infrastructure had already been stressed by the previous event, where power had been recently restored and was fragile, where trees weakened by the drought's moisture stress were more susceptible to wind damage than they would normally be, where the soil that anchored utility poles had cracked and dried under the heat dome conditions. This is the compounding mechanic that nobody is modeling in the public risk communication about this pattern. Storm damage models treat each event as independent. They calculate the expected damage from event A, then separately calculate the expected damage from event B, then add them. But the actual damage from event B is higher than the model predicts, because event B is operating on a system that event A already compromised. Trees weakened by the first MCS are more likely to fall in the second. Power lines that are under repair when the second MCS arrives get damaged again. Utility crews are already exhausted before the second event begins. The cold pool from the first event can actually seed the development of the second, in some configurations, by leaving a pool of dense, cool air at the surface that the next disturbance can use as a source of low-level convergence. The serial nature of the threat is what makes the first 2 weeks of June 2026 categorically different from a single major weather event. This isn't being framed that way in the current coverage, which is treating each individual day's storm risk as a separate story. But the atmosphere isn't creating separate stories. It's running one long story, with a new chapter arriving every 36 to 48 hours along the dome's perimeter. There's research on this compounding dynamic from an unexpected direction, wildfire science. The concept of fire-weather drought, the rapid drying of fuels that makes fires more intense, has a direct atmospheric analog in the compounding of storm damage over extended heat dome periods. Park Williams, a research professor at the Lamont Doherty Earth Observatory at Columbia University, has documented how prolonged heat dome conditions change the physical properties of the landscape in ways that make subsequent events more damaging. Drought-stressed trees have compromised root systems and reduced structural integrity. Soils that have cracked and dried don't absorb post-storm rainfall, So the next MCS produces flash flooding on ground that would have absorbed the same precipitation 2 weeks earlier. The landscape itself has been changed by the heat dome, and everything that comes after operates on the changed landscape. So the damage from day 12 of a Ring of Fire event is not the same as the damage from day 1. It's higher. It's higher because the landscape has been degraded, the infrastructure has been stressed, the workforce is fatigued, and the atmosphere has been providing daily top-ups of severe weather energy along the same general corridor. The compound damage from 2 weeks of this pattern isn't additive, it's multiplied. I want to talk about a specific geographic zone that I think is underweighted in the current coverage of this pattern, because the attention tends to go to the dramatic temperature records inside the dome's core and the dramatic storm imagery on the dome's outer edge. But there's a band of states that sit right in the transition zone, not fully inside the dome, not fully on the storm perimeter, that face a particular combination of threats that doesn't fit neatly into either the heat story or the storm story. Those states are, roughly speaking, Missouri, Illinois, Indiana, Ohio, Kentucky, and Tennessee. The Mid-American Transition Band. Inside these states, you have a combination that I want to describe carefully. On any given day during the first 2 weeks of June, temperatures in this band may be elevated but not record-breaking, say 93 to 98 degrees, rather than the 105 to 108 being recorded in the dome's core in Oklahoma and Kansas. But the humidity in this band is higher than in the dome's core because they're close enough to the moisture source, the Gulf of Mexico, to have significant precipitable water in the column. So the heat index, the feels-like temperature, can reach 110 to 112 degrees in Indianapolis on a day when the actual air temperature is only 94. That heat index is in the danger to extreme danger category of NOAA's Heat Safety Index, which means the risk of heat stroke with normal activity is significant. But this temperature doesn't trigger the same emergency response protocols as a 104-degree day in Tulsa. It doesn't make the same headlines. And so the public perception in Indianapolis is that they're in a hot but manageable situation, while they're actually in a physiologically dangerous one. And then the storm comes. Because the transition band, Missouri, Illinois, Indiana, Ohio, Kentucky, Tennessee, is precisely where the dome's edge is most active in a typical Ring of Fire pattern. These states are far enough from the dome's core that they have the moisture and instability the MCS events need. They're close enough to the dome that the temperature gradient is steep. They have the cape loading, and they sit in the path that MCS events take as they exit the plains and move northeast and east along the dome's boundary. NWS offices covering these states, NWS Indianapolis and Wilmington in Ohio, NWS Nashville, NWS St. Louis, are among the busiest forecast offices in the country during Ring of Fire events. The area forecast discussions coming out of those offices during the first 2 weeks of June 2026 will be worth reading closely, because they'll be the ground-level operational signal of how the pattern is actually evolving. When the forecasters at NWS Nashville's overnight shift start including language like elevated confidence in overnight MCS development and derecho parameters possible with the strongest cells, that's the operational alarm bell that the serial scenario is cycling through. The aging power grid in these states compounds the exposure. Much of the distribution infrastructure in the industrial Midwest was built in the 1950s and 1960s. Utility poles and transmission lines that are now 60 to 70 years old. The American Society of Civil Engineers Infrastructure Report Card gave the U.S. energy infrastructure a C- grade in 2025. That grade reflects the age and condition of the distribution infrastructure in precisely the states that sit in the Ring of Fire transition band. An MCS event driving 90-mile-per-hour winds into 60-year-old infrastructure is a categorically different risk proposition than the same storm hitting 10-year-old hardened grid components. There are also specific NEXRAD radar gaps in parts of the transition band that affect the early warning system. Radar coverage in the lower atmosphere, the kind of scan angles that detect low-level rotation and developing bow echo signatures, has known limitations in certain terrain configurations. I'm not going to overstate this because the NEXRAD network is one of the best operational radar networks in the world, and the forecasters using it are expert. But the ability to detect a developing MCS at full strength requires data from radar sites with unobstructed low-level coverage, and the terrain in parts of Kentucky and Tennessee creates shadows that can delay detection of the strongest low-level wind signatures by several minutes. In a derecho event moving at 60 to 70 miles per hour, several minutes is the difference between an adequate warning and no warning at all. This is the part of the investigation I want to be careful about, because the easiest thing to do with evidence like what I've assembled here is to slide into accusation. to say the institutions failed, the warnings were inadequate, officials were asleep. That's not what I'm going to say, because it's not what the evidence says. What the evidence says is more specific, and in some ways, more challenging than institutional failure. What the evidence says is that the institutions responsible for preparedness and communication are optimized for the pattern of risk they have historically observed. And the pattern of risk is changing faster than the institutional response cycle can match. Let me be precise about what I mean. NERC summer reliability assessments are produced on an annual cycle. The 2026 assessment was released May 19th. It found that all assessment areas were expected to have adequate resources under normal summer peak demand. It identified elevated risk under extreme conditions in 3 regions. And it defined extreme conditions in a way that models historical heat waves, multi-day events that arrive in July or August, after the grid has transitioned to full summer operations. The scenario that the first 2 weeks of June 2026 represents is not fully captured by that framework, because extreme in NERC's model is calibrated against July and August events. An extreme event in early June, when maintenance overlaps are more likely, when some generating units haven't completed their seasonal transitions, when the staffing and operational protocols are still in shoulder season mode, is in effect more extreme than the same event in mid-July. Because it's arriving when the system is less prepared for it. The National Weather Service and the Storm Prediction Center are world-class at what they do. The SPC's medium-range guidance for the June 2026 pattern is appropriately identifying the elevated severe weather risk along the dome's perimeter. But NWS and SPC communicate day by day, event by event. Their operational products, the area forecast discussion, the day 1 convective outlook, the severe thunderstorm watch, are designed to communicate the risk for specific events in specific time windows. They are not designed to communicate the cumulative risk of a 2-week serial severe weather sequence, because that is not how their products are structured. The product suite that exists for communicating your region faces elevated risk of repeated severe MCS events for the next 14 days as a persistent blocking pattern drives serial derecho activity along the dome's perimeter doesn't exist. The individual event products exist. The aggregate pattern risk communication doesn't. This is not a failure. It's a gap. And the gap exists because the serial compound event, the 2-week blocking pattern that combines interior heat dome, perimeter storm cycling, grid compound stress, and flash drought simultaneously, is a relatively recent phenomenon at the frequency and intensity levels we're now observing. The institution response cycle, the research, the product development, the testing, the training, the public communication takes 5 to 10 years. The atmospheric pattern has changed faster than that. So what we're left with is a situation where the individual components of this threat are well monitored and well communicated by the institutions responsible for them. But the compound, integrated picture, the thesis of this investigation, isn't assembled in any single place that the public can access in real time. That's what this channel exists to do. I've spent some time in the comments sections of weather coverage of patterns like this one. And I want to address directly what's circulating because the people who believe these claims deserve an actual answer, not a dismissal. The claims I see most often take 2 forms. 1. This is weather modification, that some agency, some government, some technology is deliberately engineering the ring of fire pattern for unstated purposes. 2. The severity being described is exaggerated, that weather patterns like this are routine and the coverage is hype designed to generate clicks. Let me take them in order. The weather modification claim. The most commonly cited technology in these discussions is HAARP, the High Frequency Active Auroral Research Program in Alaska. HAARP is real. It exists. It's operated by the University of Alaska Fairbanks and transmits high-frequency radio waves into the ionosphere for research purposes. Its maximum transmission power is 3.6 megawatts. A single afternoon thunderstorm releases energy equivalent to roughly 13 kilotons of TNT. A full heat dome system contains energy equivalent to several nuclear weapons detonating simultaneously, continuously, for weeks. HAARP's maximum output is to a mid-latitude heat dome, roughly what a birthday candle is to a steel mill. The energy orders of magnitude don't make contact with each other. This is not opinion. It's a calculation from physical constants. The honest version of the weather modification concern, the one that has peer-reviewed scientific substrate, is about urban heat islands. Dense, built-up urban environments genuinely do modify local temperature fields. The urban heat island effect is documented, it's significant in large cities, and it does interact with synoptic scale weather patterns in ways that research is still characterizing. That's not weather control, but it is a real human fingerprint contribution to the intensity of heat dome events, particularly in urban areas. If you're looking for the human element in this story, that's where the physics actually lives, not in directed energy weapons, but in the thermal mass of concrete and asphalt and steel that traps and re-emits solar radiation in city centers. The second claim, that this is routine, that the coverage is exaggerated. Here I want to be careful, because there's a version of this criticism that's legitimate. There are channels and outlets that routinely overstate weather risk. There are meteorologists on social media who use every high-pressure ridge as an opportunity to produce alarming content, regardless of whether the specific setup warrants it. Healthy skepticism of weather hype is rational. I'd rather you be skeptical than credulous. But here's what I'd ask you to hold in the other hand while you apply that skepticism. The 2012 heat wave, which was the reference event we've returned to throughout this investigation, destroyed $41 billion in crops, killed over 80 people in direct heat deaths, generated a 3.7 million customer power outage from a single derecho event, and produced what researchers now describe as a once every 5 years event using a probability baseline that wasn't true before 2012. The 2020 Iowa derecho was $11.5 billion in 14 hours. The June 2025 tornado and derecho complex was $875 million and 7 deaths over 4 days. Those are not routine numbers. Those are the numbers this type of atmospheric pattern produces when it runs. The current setup has the atmospheric ingredients for a pattern in this category. Whether it fully delivers on those ingredients, whether the blocking is persistent enough, whether the individual MCS events track over populated areas, whether the grid holds, those questions have answers I can't give you at this range. What I can give you is the honest assessment of what the setup looks like, what history says it's capable of, and what the grid watchdog said about the region's resilience under the exact kind of extreme conditions this pattern creates. And what all three of those things say together is that the first 2 weeks of June are worth watching closely.
What I can give you is the honest assessment of what the setup looks like, what history says it's capable of, and what the grid watchdog said about the region's resilience under the exact kind of extreme conditions this pattern creates. And what all three of those things say, together, is that the first 2 weeks of June are worth watching closely.
I want to present this honestly. An honest presentation means giving you 3 distinct ways to read what's happening. Not because I'm unsure of the physics is settled, but because the question of what this particular setup will actually produce involves enough variables, enough atmospheric uncertainty at medium range, that intellectual honesty requires presenting the range. So here are the 3 interpretations, and I'm going to give each of them genuine weight. The first interpretation, manageable, within historical variability, the most benign reading of the June 2026 atmospheric pattern is this. The ridge is real, the temperature anomaly is real, and the severe weather risk along the dome's perimeter is real, but it resolves without producing the aggregate compound damage scenario I've been describing. Here's why that interpretation is legitimate. Heat domes in early June are not unprecedented. The June 21st to 25th, 2025 heat dome, which drove the Fox Weather Forecast Center's warning about above normal temperatures for the central and eastern U.S., resolved without a major power grid failure in any of the affected regions. The July 23rd, 2025 heat dome affected an estimated 160 million Americans and produced significant public health advisories, but did not produce a cascade of grid failures. These events were serious, they were not catastrophic. The NERC 2026 assessment's confident statement that all assessment areas have adequate resources under normal conditions reflects a grid that has genuinely improved. 58 gigawatts of new generation capacity added since summer 2025, including 16.4 gigawatts of solar and 14.7 gigawatts of battery storage. The June 2025 tornado and derecho complex was a high-impact event, but it did not produce the kind of cascading power grid failure I've described as a worst-case scenario. The mutual aid system functioned. Restoration was completed in a reasonable time frame. The NWS warning system performed. People got warnings. Most people used them. This interpretation says the setup is loaded, the risk is elevated, the conditions are uncomfortable and potentially dangerous, but the system has more resilience than the worst-case framing suggests. The grid has added capacity. The NWS has better tools. The public is more informed about heat risk than it was in 2012. Events of this type have occurred before and been managed. This is not a straw man. It's a fair reading of the evidence. And I want you to hold it seriously because the temptation in weather coverage is always toward the alarming reading. The alarming reading gets watched. The measured reading gets scrolled past. But the measured reading has genuine evidence behind it, and the people planning their lives around this forecast deserve to know that. The second interpretation. The weight of the evidence. Here's where the published literature and the operational data actually point. The compounding of heat dome persistence, serial MCS activity, grid stress, and flash drought is not a hypothetical scenario assembled for this investigation. It is documented in the 2012 summer, partially observed in June 2025, and described explicitly in the research on compound climate events, the Nature Geoscience analysis of flash droughts, and the deep sky climate modeling of heat wave probability. The probability of a heat wave of 2012's magnitude in the American breadbasket has increased by a factor of 20 since the 1990s. That's not an outlier claim. It's the central finding of the research. The NERC 2026 assessment's identification of MESO, PJM, and ERCOT as high risk for energy shortfalls under extreme conditions is based on modeling that uses historical extreme weather as the reference. If the frequency of extreme events has increased, as the research documents, and the grid's reserve margins under extreme conditions are already flagged as high risk, then the probability of a grid stress event during a ring of fire pattern in early June is higher than it would have been during a comparable pattern 10 years ago. The intermediate interpretation says this pattern will produce significant impacts. Some regions inside the dome will experience flash drought conditions with measurable agricultural damage. Some regions on the perimeter will experience major MCS events with wind damage, power outages, and possible fatalities. The cumulative impact over 2 weeks will be larger than the impact of any single event. The grid will experience stress events in at least one of the flagged high-risk regions, and the response will be challenged by the early season timing. This is not a prediction of catastrophe. It's a prediction of significant compound impact that will require coordinated response from utility companies, NWS offices, emergency managers, and public health agencies. The weight of the evidence supports this reading more directly than either the benign interpretation or the worst-case one. The third interpretation. When the extremes align, the most concerning reading requires a specific set of additional conditions beyond the baseline pattern. These conditions are not assured, but they are physically possible, and recent trends make them more likely than they were a decade ago. The scenario is this. The blocking pattern is more persistent than the current models are indicating. Instead of 2 weeks, it holds for 3. The individual MCS events along the dome's perimeter are not just significant but derecho producing, with multiple events tracking through the MESO and PJM footprint in quick succession. The grid stress from heat demand and storm damage combines with the early June maintenance overlap to produce a rolling sequence of power outages across a 3 to 5 state area that overwhelms the mutual aid system's capacity to restore service quickly. Flash drought conditions develop within days in the Corn Belt, locking in yield losses for the 2026 growing season. And the convergence of all these effects produces a public health cascade, particularly in the Midwest transition states, where heat mortality climbs across a 2-week period rather than being concentrated in a single acute event. This interpretation doesn't require anything unprecedented. Everything in it has happened. The 2012 summer produced virtually all of these elements, just not in early June and not in a single 2-week period. The 2020 Iowa derecho showed what a single MCS event could do to a state's agricultural capacity and power infrastructure in 14 hours. The 2021 Pacific Northwest event showed what an early season heat dome at 4 standard deviations above normal could do to agriculture. The 2012 derecho aftermath showed what happens to human health when post-storm power outages overlap with extreme heat. The third interpretation assembles these documented outcomes into a single compound sequence. It doesn't require the atmosphere to do anything new. It requires it to do several already documented things at the same time. What data would distinguish between these 3 interpretations over the next 2 weeks? 3 specific things. First, the persistence of the blocking pattern. If the ridge weakens and moves by June 10th, the compound scenario doesn't have time to develop. Second, the intensity and track of individual MCS events, whether they produce organized derechos or dissipate before reaching major population centers. Third, the grid response in MESO and PJM, whether demand response programs and load management are sufficient to maintain adequate operating margins during the peak heat days, particularly in the early days of June before full summer protocols are in place. We can watch all 3 in real time. The NWS area forecast discussions from the key offices are publicly available. MESO and PJM publish their operating condition reports. The SPC's Day 1 convective outlook updates by 5:30 each morning, and we'll be watching. This section is for the people who are not watching this as a general interest investigation, but as something that directly affects their lives in the next 2 weeks. Let me break down what the pattern means geographically by where you are. If you are in the core of the dome, central and western Kansas, Oklahoma, the Texas Panhandle, eastern New Mexico, central Nebraska, the primary threat is heat. Sustained temperatures 20 degrees above normal, with possible record highs for June in the areas closest to the dome's center. Flash drought conditions will develop rapidly, and agricultural operations should be watching the 5-kilometer daily NOAA SST product for any upper air pattern changes that could indicate ridge weakening. More concretely, water use, livestock welfare, and crop monitoring should shift to daily assessment rather than weekly. Heat-related illness risk for outdoor workers is elevated to the extreme danger category through this period. If you are on the dome's inner edge, Missouri, southern Illinois, southern Indiana, western Kentucky, and Tennessee, the threat is compound. Hot enough to be dangerous, with heat indices approaching 110 degrees on peak days. Close enough to the storm perimeter that significant thunderstorm activity, including possible MCS events, could arrive on any given evening. This is the population that needs to be paying attention to both the heat advisory and the severe thunderstorm watch, potentially simultaneously on the same day. The scenario of 100-degree air and a power outage from a nighttime MCS is most likely in this band. If you are on the dome's outer edge, the northern plains, the upper Midwest, the Great Lakes states, the mid-Atlantic, the primary threat is severe weather. Daily MCS events cycling through the dome's perimeter, with the potential for derecho-producing events when upper-level disturbances provide sufficient forcing. The specific warning products to monitor are the SPC Day 1 Convective Outlook, the NWS Area Forecast discussions from your local office, and the Koch's NEXRAD radar at Old Hickory, Tennessee, the CLOT at Chicago, the KILN at Wilmington, Ohio, the KDMX at Des Moines, Iowa, and the K2BUX at Topeka, Kansas. Those 5 radar sites cover the most active zones of the pattern's perimeter. When any of them shows a developing bow echo in the afternoon hours, the next few hours matter. If you have elderly family members in any of these zones, particularly in the Midwest transition states, this is the period to check in proactively, not reactively, after the power has been out for 12 hours in 98-degree heat now. The heat mortality dynamic I described in Part 10 is real, and it is preventable with advanced preparation. Cooling centers, stay-in contact plans, battery-powered fans, stored water. The city and county emergency management websites for the MESO and PJM states will have updated heat emergency protocols. Find them before you need them. Emergency managers in the affected states are already working this pattern. The state emergency management agencies in Missouri, Illinois, Indiana, Ohio, Kansas, Oklahoma, and Texas all have public readiness communications. Those communications will intensify in the coming days as the pattern develops. They're worth following, even if the language is cautious and institutional and doesn't capture the full compound picture this investigation has assembled. Institutional caution is a feature when it prevents panic. It's a limitation when the pattern warrants preparation above the baseline. I want to return to the grid for a moment, because there's a specific dimension of the reliability challenge that I don't think has been adequately explained in the coverage of NERC's assessment, and it matters for understanding what happens if the pattern develops toward the intermediate or worst-case scenarios. The grid managers, the operators at MESO, PJM, and ERCOT, have a toolkit for managing demand during heat events. It includes conservation requests, which ask customers to voluntarily reduce consumption. It includes direct load control programs, which give utilities the ability to cycle off on large loads like water heaters and air conditioning units remotely, with customer consent. It includes demand response programs that pay large industrial customers to reduce consumption during peak events. And at the most extreme, it includes controlled load shedding, rolling blackouts where power is cut to sections of the service territory on a rotating basis to prevent an uncontrolled total grid collapse. Controlled load shedding is the option of last resort. It produces predictable, managed outages rather than cascading, uncontrolled failures, but it is deeply disruptive. During a heat event with 100-degree temperatures, controlled load shedding in a dense urban area, even if it's rotating and managed, can rapidly produce the post-storm heat mortality scenario I described in the 2012 analysis. People in the cut zone without air conditioning, in heat index conditions above 100 degrees, in housing stock that isn't thermally resilient, face heat stroke risk within hours. The grid operators know this. They are not cavalier about it. But they're managing a system where the tension between preventing uncontrolled grid collapse and avoiding the health consequences of controlled load shedding doesn't have a clean answer when both scenarios are simultaneously on the table. What makes the early June timing specifically challenging, and this is the NERC maintenance overlap point made concrete, is that some generating units offline for seasonal maintenance can't be brought back to full capacity in the time window that an early June heat emergency allows. A unit that's offline for planned maintenance work on June 1st can't necessarily be back at full capacity by June 8th. The work has to be completed in sequence. You can accelerate some of it. You can't accelerate all of it. And the grid operator has to manage peak demand with whatever capacity is actually available on the day the temperature hits 105. ERCOT has been here before in a different season. The February 2021 freeze hit during a period when a large fraction of the generating fleet, including wind, natural gas, and coal units, was offline for winter maintenance or experienced cold weather failures. The result was 4 million customers without power for days in temperatures below zero. The parallel to an early June heat dome is not exact. The February freeze involved generating unit failures from cold, not planned maintenance. But the underlying structure is similar. A weather event arriving at a time when the generating fleet's available capacity was below its summer maximum. The DE, in response to the NERC assessment's maintenance overlap concern, has used its Section 202C authority under the Federal Power Act to order 6 coal and gas plants to remain operational through late May and June, covering precisely this spring to summer transition window. Those 6 plants were not even counted in NERC's anticipated resources for summer. They're only still available to the grid because the DOE stepped in. As the Independent Women's Forum analysis of the NERC assessment noted, NERC's own data show that most of what's being added to the grid cannot be counted on at peak demand. Solar goes offline at sunset, right when the hottest part of the day is transitioning to the warmest night. Battery storage has capacity limits. A 14.7 gigawatt battery fleet sounds substantial until you're trying to run PJM's load through a 3-day heat dome with 100-degree overnight lows. And the 6 coal and gas plants the DOE has kept online are at some point going to go offline. The question is whether the weather has cleared by then. Let me be specific about the state of the evidence as this investigation closes, because the pattern is still developing, and the honest accounting of what's confirmed versus what's still uncertain is part of the value I want to deliver here. What is confirmed and unambiguous? A ridge of high pressure centered over the central United States is building and will persist through at least the first 10 days of June 2026. This is documented in the WPC Extended Forecast discussion from May 30th and in the SPC Day 4 through 8 convective outlook from the same date. The large-scale pattern is not in dispute. The ridge will produce above normal temperatures. The WPC's language is a dome of above normal temperatures accompanying it. Temperature anomalies of 15 to 20 degrees above normal in the dome's core are within the range the established pattern supports. Along the dome's perimeter, severe weather risk is elevated. The SPC medium-range guidance identified moderate to strong instability developing in the vicinity of the ridge, with isolated severe storms possible even on days when the large-scale forcing is limited. When upper-level disturbances provide additional forcing, organized MCS events, including potential derecho-producing systems, are within the range of what this setup supports. The NERC 2026 Summer Reliability Assessment has documented that MESO, PJM, and ERCOT face high risk of energy shortfalls under extreme conditions. These regions are the same regions under or adjacent to the heat dome. What is genuinely uncertain? The persistence of the blocking pattern beyond day 10. Model guidance at medium range has known limitations in resolving the exact longevity of blocking events. The ensemble spread on this question is non-trivial. The WPC's slowly east language reflects uncertainty about timing, not certainty about persistence. The specific geographic tracks of individual MCS events. Convective initiation location and subsequent storm motion are highly sensitive to small-scale boundary features that medium-range models can't resolve. The difference between a derecho that tracks through a major metropolitan area and one that tracks through rural farmland is the difference between hundreds of millions and tens of billions of dollars in damage. The grid's actual response under compound stress. NERC's assessment identifies risk under extreme conditions. Whether the actual June 2026 pattern constitutes extreme conditions in NERC's framework, and whether the response mechanisms, demand response, load control, the DO extended generating units, are sufficient to prevent controlled load shedding in any region depends on variables that will only resolve in real time. What comes next? Watch the SPC Day 1 convective outlook each morning. Watch the WPC's updated extended forecast discussions, which are posted twice daily at College Park. Watch the area forecast discussions from NWS Chicago, NWS Indianapolis, NWS Nash Wilmington, and NWS St. Louis. Those 5 offices are the operational ground truth for the most vulnerable transition zone states. And watch the MESO and PJM daily operating condition reports, which are publicly available, and tell you directly whether the regional grid operator has moved to a heightened operating state. These are not difficult sources to access. The NWS website has all of them. The SPC Outlook is at spc.oa.gov. MESO and PJM post their operating condition reports on their public websites. The data that tells you how this pattern is actually developing is freely available to anyone who knows where to look. And that's something I want to say plainly. Part of what this channel does is translate the raw operational data, the area forecast discussions, the CAPE analyses, the NEXRAD radar signatures, the NERC operating conditions, into language that doesn't require a meteorology degree to understand. Not because the people in that field aren't doing their jobs. They are. But the gap between the technical operational data and the public's ability to understand what it means is real. And in a compound event like this one, where the story isn't any single product's forecast, but the integration of 5 or 6 different data streams across multiple systems, that translation matters. I started this investigation with a specific claim, that the first 2 weeks of June will be unlike anything most of America expects. Not because the atmosphere is unprecedented. Most of what I've described has happened before, in some form, in some combination. But because the expectations of most Americans about what the first 2 weeks of June look like, a warm but transitional period, an early summer stretch that's hot but not catastrophic, a time when the real heat hasn't arrived yet, are calibrated against a baseline that's no longer accurate. The baseline is a seasonal one. June isn't supposed to be when the heat dome locks in. June isn't supposed to be when the derecho factory runs at full production. June isn't supposed to be when the grid faces the stress that NERC models for August events. But the atmosphere doesn't read the calendar. The ridge that's building right now doesn't know it arrived 6 weeks early. And that mismatch between what the atmosphere is doing and what the preparedness systems, the grid protocols, the institutional frameworks, and the public expectations are calibrated for is the actual danger in this 2-week period. Not the heat alone, not the storms alone, not the grid alone, the mismatch. The 2012 summer taught us what this combination is capable of. $30 billion in combined losses. 82 direct heat deaths, 3.7 million customers without power from a single storm. 34 post-storm heat deaths in the dark in 100-degree heat. A flash drought that destroyed $41 billion in agricultural production in the breadbasket of the country. And since 2012, the probability of the heat dome component of that scenario has increased by a factor of 20. The demand load on the grid has increased by more than 11 gigawatts in the last year alone. The infrastructure delivering power to the most vulnerable populations hasn't been comprehensively upgraded. I'm not going to tell you this is going to be the worst weather event in modern American history because I don't know that, and anyone who tells you they do know is wrong. What I'm going to tell you is what the evidence actually says. This setup is capable of producing compound impacts at a level that most of the country isn't currently prepared for. The mechanisms are established. The historical cases are documented. The grid vulnerabilities are in writing from the nation's own reliability authority. And the atmospheric setup is in motion right now, building over the center of the country, with its perimeter already loaded and the temperature gradient already steepening at the edge. The data doesn't tell us which of the 3 interpretations is correct. What the data tells us is what each one costs if it turns out to be wrong. There's a question I'm holding as this pattern continues to develop, and it's the one I want to leave you with, because it doesn't have an answer I can give you today. The question is about the gap between what NERC's assessment found: adequate resources under normal conditions, elevated risk under extreme conditions, and what this early June pattern represents for the 3 high-risk regions at its center. Is this pattern, arriving before the seasonal transition is complete, inside the definition of extreme that NERC modeled? Or does it fall into a category that the assessment framework hasn't fully addressed yet? John Mora, NERC's Director of Reliability Assessment and System Analysis, said in late May, "The improved conditions we're seeing shouldn't be interpreted as saying that overall reliability risk is declining." He said it carefully, in an institutional context, with the hedging that institutional language requires. But the message is plain enough.
We're watching. The pattern is moving. When it resolves, when the ridge lifts, when the storms cycle through, when the grid response data comes in, when the crop assessments start, we'll be back with what it actually produced versus what the setup said it was capable of. And if the pattern delivers toward the higher end of what the evidence says it can do, we want you to have had this picture before it arrived, not after. The first 2 weeks of June are not a background story, they're the story.